Welcome back to the series on statistics. In this video, we're going to cover our second continuous probability distribution, the normal distribution. This is kind of going to come out of nowhere because in the last video, we talked about our first continuous probability distribution, which is the uniform distribution. It's the simplest probability distribution, or the simplest continuous one at least, maybe the simplest. And as far as its applications go, uniform distribution is almost useless. There are some specific instances where it is useful, particularly in signal analysis, things like that. The only time I've ever used a uniform distribution outside of statistics homework problems was trying to generate random numbers, but the procedure for that went, okay, so you have a random number generator, a pseudo-random number generator, that generates a value between 0 and 1. So you already have your random number. Now multiply it by the length of the interval to get your uniform distribution. So it's like, that's not really using the distribution. It's just multiplying by the length of the interval to spread that proportion out and get a random value between two bounds. In contrast, the second probability distribution that we talk about, this one, the normal distribution, is arguably the most important probability distribution in all of statistics. It has applications in almost every field that you can think of, and pretty much every probability distribution that comes in statistics after this one is just derived from this one. So it's like, okay, here's something that's almost useless, and now here is something that is useful for literally everything you could possibly think about. So we're going to talk about why that's the case, and we're going to get into deriving this distribution, but if you like applications, start getting excited now, because this is basically unending what you can do with the normal distribution. Okay, so let's derive the normal distribution. We're asked to consider the case of a dartboard, and suppose that I'm halfway decent at darts. So I went ahead and added some marks on this dartboard here that are representative of where my darts would land. Supposing I'm pretty good at darts, most of them are going to be near the center, and then as you get further and further away from the center, the probability of the dart landing in this region out here is going to get less and less and less. So if, for example, you thought of how many darts would be in the first circle, there's going to be a lot more than the second circle. And it looks like once we get to the second circle, we get 1, 2, 3, 4, 5, 6 that are purely in the second circle, and then it drops out to about half that once we get to the amount of darts that wind up in the third circle. So the probability is decreasing as we get further away from this mean. And so we're asked, how can we come up with a probability density function to model this situation, to model the probability of me hitting a particular region of the dartboard? And so the way that we would express this mathematically is we'd say the probability of, let's just say, for example, the probability of x being between -1 and 1, and y being between -1 and 1. This is going to be equal to the area under some surface, which is given as a function of x and y, with respect to x and y. And so this function here is going to be the probability density function that we're looking for. And what is it going to give us? Well, it's going to give us the probability of a dart landing in some region that might look something like this. Let's say that this is 1, -1, 1, -1 here. Then this function that we're after is going to give us the probability of a function landing in this region. So how could we figure out what this function actually is? Now you might be thinking, this is just an impossible question. We have no information here. We're starting from scratch. This is so abstract. How could we even proceed here? Well, the answer is that we need to make some assumptions, and we need to start thinking about the situation, and we're just going to tackle this sort of bit by bit. And so what do I mean by that? The first question I want to ask is, what if we just wanted to consider the probability of us missing in the x direction? Well, we could write that, like, let's say we want the probability of, let's pick two different values here. Let's say the probability of x being between 1 and 2. And so how can we figure this out? Well, if you just want the probability of x being between 1 and 2, let's just say that this is, well, we already said that this was 1, so let's say this is 1. I'll do this in a different color so you can see. This is 1. and then let's say 2 is to be about the width of the box. It's somewhere over here. If we want the probability of x being between this x value and this x value, but the value of y doesn't matter, then what we want is the probability of the dart landing in this region here, which is going to extend forever in both directions. And so this region on the graph is going to represent the area with which we're concerned about. And what we want to do is we want to figure out, I'll put some dots there so you can see this goes forever, is we want to figure out how can we express this in terms of our probability density function. And so if we want to express this in terms of the probability density function, we need to integrate under the surface f of x, y. And then first thing that we need to do is we need to integrate with respect to y, and we need to integrate over all real numbers in both directions, because it doesn't matter where the dart lands in the y direction. We are simply concerned of the probability of it falling between 1 and 2 in the x direction. And so if we wanted to evaluate this, we would write this region as going from negative infinity to infinity with respect to y, and then going from 1 to 2 with respect to x. And now I'd like you to consider if we were to integrate over all of these possible values. So in other words, if we were to take, let's say, the double integral over all real numbers in r squared of this f of x, y, of this probability density function here, if we were going to do this, if this is a valid probability density function for this distribution, then this needs to evaluate to 1. That just comes from the definition of a probability density function. If you're integrating over all possible values, that's going to represent the probability of all possible outcomes, of at least one of those outcomes occurring. So that probability needs to be 1. And so if this is going to be equal to 1, then I'm sure that you will agree that this probability needs to be less than 1. In particular, if integrating here is going to give us 1, my point is that this integral right here, this negative infinity to infinity of f of x, y with respect to y, this shouldn't be something that we're concerned about, because this is not going to diverge, because we know by the time that we work out this entire integral, this might result in another function or something, but at the end of the day, if integrating over from negative infinity to infinity for both variables is going to give us a constant, then this is certainly going to give us a constant that's going to be less than 1. And so this function right here, or this integral right here, this integral from negative infinity to infinity of f of x, y, our probability density function with respect to y, there's a special name for this. This is called the marginal probability density function of x, and it's denoted somewhat like this. And so this is going to give us this is a separate probability density function that just deals with x, but this would be how you evaluate it. And I hope that makes sense from the graph. I'm going to make another video on marginal probability density functions from things like what we are considering right now, which is a joint probability distribution, but I don't think this is that big of a leap. It should be not too complicated. Now, I mentioned earlier that if we want to proceed, we need to make some assumptions. And so what assumptions can we make about this situation, about this probability distribution? Well, the first thing I can think of, there's two, is the first thing is that the distance is the only variable that affects the probability. I think this is a reasonable assumption to make. Essentially, what we're saying is that the probability of hitting here on the dartboard is exactly the same as hitting here, or anywhere else where the distance from the target is equal. This is a reasonable assumption to make in real life. This might not be the case. There could be some confounding variables. It could be more likely that you hit lower on the dartboard due to gravity, something like that. But it's a reasonable assumption to make. It's at least probably correct, or approximately correct, I should say. And so let's make that assumption. And the second assumption that we want to make is that the degree to which you miss in the x and y directions is independent. This is even more of a reasonable approximation, I think. What this is telling us is that if I miss somewhere over here in the x direction, or something like that, that tells me nothing about where I'm going to land in the y direction. And I think you would agree that that is a reasonable assumption we can make for this situation. So with that in mind, we can move forward a little bit. Why do we want to make these two assumptions? From the first assumption, so I'll go ahead and denote this from 1. From the first assumption here, we know that there must be some other function that exists, call it g of x, or g. And this function is exactly equal to this one, evaluated with x and y. But this function, instead of taking a xy pair as input, is going to take x squared plus y squared, which is proportional to the distance from the origin. This just comes from the Pythagorean theorem. This is going to be the square of the distance from the origin, but it is going to be proportional to the distance from the origin. So there must be some other function that exists out there such that this function, when taken the distance as the input, which is the only variable that affects the probability, will be equal to our probability density function. The second assumption that we want to make is that the degree to which you miss in the x direction and y direction is independent. Why do we want to make that assumption? Well, what this is going to tell us is that if x and y are independent, the degree to which you miss in the x and the y directions is independent of one another, then you could think of taking this idea of marginal probability distribution, or probability density function for x. So this is a different function that when integrated over is going to give us a probability of landing somewhere in the x direction. And if this is confusing, just try to notice we're saying that the probability of x being between 1 and 2 is given by integrating over this function value, whatever it is, from 1 to 2. And that is exactly what the definition of a probability density function is. So this expression here is what we're integrating over. And so this expression is a probability density function for x. This is integrating over this is going to give us a probability of landing in some range of x values. And so if x and y, if the degree to which we miss in the x and y directions is independent, then this function, f of x, y, is going to be proportional. Well, actually, it's going to be exactly equal to the marginal probability distribution of x multiplied by the marginal probability density function for y. And the reason that this is true is because these two errors are independent. And so what we know from probability is that we have the probability of some event multiplied by the probability of another event. If the two events are independent, then multiplying them together will give the probability of both events. So if we want the probability of landing in some range of x values and the probability of landing in some range of y values, then we could just simply take the product of the probability of landing in those range of x values and the probability of landing in the range of y values. And so we know that this probability density function for our situation here is going to be equal to the product of these marginal probability density functions for the individual variables. So the next step we could take here is if these two expressions are both approximate or both equal to the same thing, we could set them equal to each other. And so what we're going to get here is that the marginal probability density function for x multiplied by the marginal probability density function for y is going to be equal to some function g that is proportional to the distance from the target. And now the next step that we need to take is we need to say let x equal 0. And what's going to happen here in this situation? Well, here on the left side, we have the marginal probability density function of x evaluated at x. And so what's that going to give us? Well, if we look back at our equation, this is what we have for our marginal probability density function for x. We're integrating over all real numbers, some function involving x and y with respect to y. And so there's only two possibilities that could occur here. We're either going to get a constant, or we're going to get a function that involves x. And once we pass a constant like 0 into a function that involves x, it's just going to give us a constant. And so either way here, if we already get a constant here, then we're done. If we get a function involving x, then what we're doing is we're passing 0 to that function, and we're going to get a constant either way. And so this is just going to be some constant. And so we're going to get some constant multiplied by the marginal probability density function of y is going to be equal to some function of x squared. Or in other words, the way that we could write this is that the marginal probability density function of y is going to be proportional to, here, I forgot I'm setting x equal to 0, so this is going to be y squared. Y squared. This is going to be proportional to some function involving y squared. And similarly, if we are to let y equal 0, then what we will find is that the marginal probability density function for x is going to be proportional to that same function involving x squared. And what do we know about the product of these marginal probability density functions? They're going to give us our original probability density function. And so what we know from this is that the function that we're after here, f of xy, which we also know is equal to g, this function that we're defined as g of x squared plus y squared, we know that this function is going to be equal to this one, which is proportional to g x squared multiplied by g of y squared. That's just the product of these probability or marginal probability density functions. And so what we're interested in here is figuring out what g of x is, or what this g function is, because we know that that is equal to our original probability density function. And so we simply need to figure out some function that models this behavior right here. And I encourage you to pause the video and think about what function, when you pass x squared plus y squared to the function, is going to be proportional to that same function evaluated at x squared multiplied by that same function evaluated at y squared. All right, so hopefully you pause the video and give that a thought. What is this function going to be? We should be pretty well acquainted with this from algebra. This is just the exponential function. So if you take some e to the x squared and you multiply this by some other constant, e to the y squared, what are you going to get? You'll get ab, which is just a constant, multiplied by e to the x squared plus y squared. And so this is proportional to these. In fact, in this case, they're exactly equal. And so we know what function we are looking for here. We have determined that g is going to be the exponential function. Now, just to solidify this a little bit, if we want this to be applicable to different scenarios, then we want to say that our probability density function here is going to equal, we can have some constant out front. That's a very common transformation that you would apply to these probability density functions. And there's also going to be some constant in the exponent here. And so we'll do negative b multiplied by x squared plus y squared. And we have found our probability density function for this situation. This value here, this a here, this is just some normalizing constant. As we mentioned in the beginning, if we want this to be a valid probability density function, then the area underneath this curve, or the surface, I should say, over all real numbers needs to be equal to 1. And so a needs to be modified in order to make that true. Because, well, we don't know that yet, but we can imagine that that could be the case. We can imagine if we integrate over this function here over all real numbers and it wasn't equal to 1, then we would need some constant here to make it equal to 1 and make it a valid probability density function. And what is this constant doing here, this negative b? Well, we know that this needs to be a negative value, particularly for our situation, because as we increase the value of the distance here, this quantity here is proportional to the distance from the target, we want our probability to decrease. And so we know that there needs to be some negative here. But this constant here, you could think of it in two ways. You could think of it as a better player, the probability would decrease quicker. It would decrease more quickly, or it would decrease faster as they moved further from the center than a worse player. You could think that the probability of a terrible player landing out here, like me, that could be a substantial probability. And so your b value, you would want it to be smaller, since that would represent a slower rate of decrease in probability as you got further from the center. But if your b value in that equation was greater, then your probability of hitting a particular region would decrease faster as you got further and further away from the center. So you could think for an expert dart player, the probability of them hitting over here would be negligible. Whereas for me, that would definitely not be negligible. And so you could think of it that way, or you could think of this b as some constant. I saw this on the stack exchange, but this could be some constant that's representative of the units with which you're measuring. For example, if you were measuring this in terms of centimeters, then you could imagine that the probability would fall off much faster than if you were measuring in millimeters. And so there's several different interpretations of this, but in order to sort of generalize this idea, we want our probability density function to have these constants so that we can modify the probability density function to fit different various data sets. All right, so there's two natural questions that should arise at this point, which is number one, why are we talking about darts in the first place? How useful is this idea? And number two, where do we go from here? So to address the first problem, we found a probability density function to represent the game of darts. Congratulations, that's great. How useful is that? Well, since we've dealt with this in such abstract terms, what are we really representing here with this probability density function? We're representing a probability density function that models a situation where data is clustered around some center value, and then as you get further and further away from that center value, the probability decreases. So you can imagine that this describes tons of phenomena in the real world. If you talk about heights, the majority of people are clustered around some range of values, some average height. So you could say like maybe from 5'7" to 6 foot. That would be the vast majority of all the United States men that you would encounter, for example. But as you got further and further off to the tail ends, for instance, as you get up to like 6'5" or 5'2", you're going to find almost no U.S. men who are that height. It's going to be very, very unlikely that you would find people in that range. And there's dozens and dozens and dozens of other phenomenon that sort of exhibit this property, where the majority of the data is clustered around some mean and then sort of peters off slowly as we get off to the ends. And for some instances, it could peter off more quickly. This just goes back to the darts analogy where we're talking about someone who's very good at darts. The probability of them hitting near the edge of the dartboard is very, very low. But somebody who's terrible at darts, it could be a little bit higher. And we know how to deal with that with this probability density function. We have to modify this b value. And so this could be descriptive of several different natural phenomena. And it's not just darts. And so the reason that we're talking about darts is actually going to go into the second question, which is where do we go from here? We have our function, right? We have some probability density function that exhibits the behavior. In the next part of this video, we're going to take this a step further, and we're going to figure out what A is, and we're going to figure out what B is, which is crazy that we could do that. In my opinion, it's crazy that we got this far. We started from literally nothing, which is think of a dartboard, let's come up with a probability density function to model the situation. And we did it. We did it by making some assumptions. And so we're going to take this a step further and really solidify this and make it applicable to real life. But the reason that we're talking about darts is because consider the case of something else. So consider heights, for example. You can imagine that heights could be explained by a similar probability density function as we already described. The majority of heights are clustered around some mean, and then it peters off as you get to the tail ends. But that's just going to be one variable. So you could think the probability of your height being, we have to say between two bounds. So the probability of your height being between A and B is going to be equal to the integral from A to B and then we'd have some probability density function, but only of one variable. So this would be a e to the negative b x squared, for example. Or I should say h squared with respect to h. I encourage you to pause the video and try this out. Don't rake your brain over it too hard. Maybe 2 minutes tops. Because the thing is that after you take the a out of here, this becomes a non-integrable function. You actually cannot take the antiderivative of this function. It's not possible with elementary functions. You can't do this with any combination of algebraic functions. It's It's not integrable. And so that's why we're talking about darts. It's because darts is a situation in which we're dealing with a joint probability density function that takes as input two variables. And for reasons we're going to discuss now, you actually can integrate this given some situations, but you can't integrate this. And so that's why we're talking about darts. That's another reason why we're talking about darts. It's a good analogy, but also because we can actually integrate this and really specify down to a T what we mean by this probability density function, really get it into concrete terms. So that's what we're going to do now. All right, so that's going to be our next step here. We're going to try to turn this candidate for a probability density function into a valid PDF. And the way we're going to accomplish that is by solving for what we want our A to be. Now, you might ask why we need to do that. The reason is because if we want this to be a valid PDF, then we want the double integral over all real numbers in R2, f of xy. We want this to be equal to 1, because this is going to represent the probability of at least one of all possible outcomes occurring. And so that's going to be 100%. We need this to be equal to 1 for this to be a valid PDF. And I encourage you to watch my last video on valid PDFs if you are curious about why that must be the case. Talk about that a little bit more in depth. For now, I think this is sufficient. So here we have this candidate for a PDF, and so we want to integrate over this in order to make sure that we can restrict that area underneath the surface produced by f of xy such that it's equal to 1. Now, you might notice that I have an exponent here of a squared term. That's just going to make the math a little bit easier. And I encourage you to realize that this is not that big of a leap. If this is a constant, then it's squaring it is also going to be a constant, so we could just let this be the square root of this one, for example. They're both just constants. They're going to wind up being constants, so it's not that big of a deal. If you're wondering why I want to turn this into a squared and why it's going to make the math easier, essentially what we have here is the product of two distributions like this, but for different variables. That's essentially what we're dealing with here, and that should make sense because we are dealing with marginal probability density functions that are independent. And so taking the product of two of them should give the probability density function for the joint distribution. And so that should make sense. And so that's why we have this a squared here. It's why it's going to make the math easier. Now let's go get to the business of actually figuring out what this a value needs to be to restrict this area to be equal to 1 and make this a valid probability density function. All right, so let's get into this. This is the idea here. We want to restrict this area to be equal to 1, or I guess in this case it would be volume under a surface. And so how are we going to actually do this? Well, we have to compute the double integral over all real numbers, so negative infinity to infinity. And here I'm going to pull this a squared out front because it's just a constant. And then we have inside here we have e to the negative b x squared plus y squared. And then we have dx dy, and we want this to be equal to 1 to turn this into a valid PDF. Now, as I already said, this is a non-integrable function, but the thing here that happens when we take the product of two of these probability density functions that are representative of the marginal probability density functions for each of these variables of the surface, when we take their products, what we could do is we could convert these to radial coordinates. And the reason that we want to convert this to radial coordinates is because it's going to allow us to use u substitution to actually compute this integral. And why would converting this to radial coordinates allow us to use u substitution? Well, the reason is, if you imagine on a coordinate grid, let's say that we have the x-axis here, y-axis here. If you want to consider what dy dx is, or dx dy, that's just going to be some small change in x multiplied by some small change in y. And so these are infinitesimal quantities we're talking about, but here, you just imagine it's the area of some small box in the Cartesian plane. And so what would be the equivalent of that for radial coordinates? You could think if you had some radius r, this would be r, then we have some small change in the radius, it would be dr. And then we want another quantity here that's going to give us something like this, so that we can have the same equivalent. We want the area of some small box in the Cartesian plane, or the polar plane in this case. And so what do we need to multiply dr by in order to get this? Well, this is just going to be a small change in the arc length of the circle produced by the radius and the angle theta. And the arc length of a circle is just r theta. And so if we want to compute this area here, we want r d theta. That's going to give us the length of this edge of the box here. And so if you took the product of these, this is going to give us something that looks like dy dx or dx dy. And so we're going to use this property because it's going to give us the r here, and then in our exponent we're going to have r squared, and then that's going to allow us to use u substitution, and it will actually cancel with the r and result in an integral that is going to be solvable through elementary methods. And so that's the procedure we're going to go with. So a simple change of coordinates. Here, if we're going to integrate with respect to theta, theta doesn't go from negative infinity to infinity, it just goes from 0 to 2 pi. And then if we're integrating our radius, negative radius isn't really a thing, it's just the same radius but flipped 180 degrees, or pi radians. And so we're going to integrate from 0 to infinity with respect to the radius. And then here, we're going to have e to the negative b times r squared. That's where we're going to get x squared plus y squared is just r squared. And then here, instead of dx dy, we're going to have r dr d theta. R dr d theta. And we want this to be equal to 1. And so, as we already said, we're going to use u substitution here. So I'm just going to say let u equal b r squared. Then we have du is going to equal 2b r dr. And thus dr will be du over 2b r. So when we make the substitution, this r is going to cancel. And this is why it's going to make the integral actually work out. And so when we make the substitution, I'm going to pull this 2b out, because it's just a constant. And so we have a squared over 2b, multiplied by the double integral from 0 to 2 pi here. And here we're going from 0 to infinity. What is this going to become? This is going to become e to the negative u. And I already dealt with all of this business, so we just are left with du here. D theta, we have that this is equal to 1. How do we solve this integral? Well, the antiderivative here is just negative e to the negative u. And if we're evaluating that from 0 to infinity, I guess we should substitute back in our u. And so what are we going to get? We're going to get negative e to the negative b r squared here, evaluated at 0 to infinity. And then the rest of this is going to stay the same. So integrating here from 0 to 2 pi. And we still have this constant out front. And so what's the limit of this as r goes to infinity? Well, this is going to be e to the negative infinity, essentially, so that's just 0. And so this is just 0 minus, and then what are we going to have as this goes to 0? Well, e to the 0 is just 1, and so we have this negative out front. We get negative 1. And so this is just going to be equal to 1. I'm just going to write that now. So this whole integral is just going to evaluate to 1, and then we're integrating from 0 to 2 pi with respect to theta. And so what are we going to get here? We're going to get, that's just 2 pi. Should be simple enough. Actually, not even going to keep that. Just expect that this is going to be equal to 2 pi, this whole integral here. And so the 2's will cancel, and we'll be left with a squared over b pi, a squared times pi over b is going to be equal to 1. And so now, as we said, we have enough information to solve for a. And so what are we going to get? We get a is equal to the square root of, let's see, this is going to be b over pi. B over pi. And so we have solved for a. And so we've almost done here. We have a, but we have it in terms of b. And so we can simplify this if we make a decision on what we want our b value to be representative of. And so for that, we're going to return to the equation we've derived here. Let's see, I'm actually going to go to this one, the marginal probability density function with respect to the x and y variables for this joint distribution here. What do we want our b to be proportional to? Let's remind ourselves of the situation that we were talking about with this equation. This is the probability of somebody's height falling between two bounds, a and b. We're saying that this is going to be given by the definite integral from a to b over some probability density function that's going to follow in a very similar manner to the darts example, because this is going to be data clustered around a mean that's going to peter off as we go to the ends. And one thing that we talked about before is that this b is going to be representative of how quickly that data peters off. So the bigger that our b value is, the quicker that the probability is going to decrease. Hopefully that's obvious from properties of exponents. And so if this b is representative of the rate at which data becomes less frequent as we distance ourselves from the mean, it would be convenient to define this in terms of the variance of our data. And hopefully that's clear. If you have a very high standard deviation, a high variance, then you would want that rate to peter down slowly. But if you had a very low variance, that data is clustered very tightly around the mean, then you would want the probability to fall off very rapidly. And so since this b value is inversely proportional to the variance, meaning if we have a high variance, we want this b value to be low, and if we have a low variance, then we want this b value to be high so that the probability falls down, it's convenient to define this in terms of the inverse of the variance. And so the way that this is actually done in practice is we define it as 1 over 2 times the variance. Now, it might be a little confusing why we have this factor of a 2 in here. The reason being is just because this makes it more fitting for normal data. If we don't have this factor of a 2 here, then this tends to, the probability tends to decrease very rapidly. And so they have this factor of a 1/2 here. It's just a convention just to make it more applicable to more situations. And so if we make this substitution for our b value here, then we can return to our equation down here, and we have that our a is equal to the square root of b over pi. And so now we can define our a as the square root of, what was our b? 1 over 2 times the variance. And so this is going to be 1 over 2 times the variance times pi. And this is exactly equal to 1 over the standard deviation multiplied by the square root of 2 pi. And so we have our final sort of value for a here, and a value for b as well that's going to be defined in terms of our variance for convenience. And so what are we left with? Well, if we take our marginal probability density function that we had for x in our situation with the darts, this was centered at a mean of 0, with, I guess, given this situation, a standard deviation of 1. But if we want to generalize this so that we can apply it to several different situations, we're going to use our a value that we came up with and our b value that we came up with, such that we can apply this to situations with different standard deviations, different variances. And so if we plug in these values that we came up with, we're going to get 1 over standard deviation multiplied by the square root 2 pi. And we're going to multiply this by the e to the power of negative b here, in this case, is 1 over 2 times the variance. And then we're multiplying by x squared. Now, I'm going to change this just a little bit, because you can imagine that in several situations in real life, our data is not going to be centered at 0, like this one is. And so, thankfully, the x variable here, the variable in this equation, only appears once. So this is just a simple matter of applying a transformation to this function. And so I'm going to write PDF is equal to 1 over standard deviation multiplied by the square root of 2 pi multiplied by e to the negative 1/2. And I'm also going to pull this standard deviation here into the exponent. I'm going to get x minus whatever we want our mean to be, divided by the standard deviation squared. And so here we have come up with a probability density function that is descriptive of all of these scenarios wherein you will find a lot of data clustered around a mean that gets less and less and less probable. There's less and less instances of finding data points as you distance yourself from the means. So this is not like the uniform distribution, which has equal probability everywhere over the interval. This is going to have a much higher probability around the mean, and then it's going to dissipate as you move away from the mean at a rate determined by our standard deviation. And so we have a place in this equation where we could put a different mean if we were going to shift this to the right and left on the x-axis, so to speak. And we also have a spot where we can put a variance, or a standard deviation. And this is going to take in mind situations where the data peters off more slowly or more rapidly as we distance ourselves from whatever the mean is. And so this sort of distribution is characteristic of several natural phenomena, and this is called the normal distribution. This is a PDF, probability density function, for the normal distribution. And so if we wanted to graph this PDF to see what it actually looks like, I went ahead and did that in Desmos. And so if we were to say that this graph actually represents x as a normally distributed continuous random variable with a mean of 0, it's still centered at 0, but in this case, I used a standard deviation of 1/2. So I decreased the standard deviation such that it's more clustered around the mean here, and we can actually see the shape of the probability density function. And since I use a standard deviation of 1/2, my variance is going to be 1/4. And so this is the way that we notate normally distributed continuous random variables. As you say, it's x is a normally distributed continuous random variable with a mean of 0 and a standard deviation of 1/2, or a variance of 1/4. So keep in mind that this is the variance, not the standard deviation. And so this is a graph of what this looks like. And you can see, if we were to integrate over this, the vast majority of it's keeping in mind that we have a standard deviation of 1/2. If we look about one standard deviation away, we just take a gander here, you can see that if we were to integrate over this from -1 standard deviation to 1 standard deviation, we would get an area that looks like this. And it appears like the function is almost equal to 0 already before we even get to 2. And so you could imagine that since this function has an area of 1 from -infinity to infinity, an area underneath it of 1 from negative infinity to infinity, this seems to encompass almost a majority of the data. And so it seems like the majority of the data in this case is within 1 standard deviation of the mean here. And so that's an interesting feature of these sorts of graphs. And so I wanted to look at a couple different examples of this. And so if you look at all of these graphs, it's not exactly the same. It's not exactly as smooth as this shape, but these are real world data. This is all real world data. So this first graph here, we have SAT scores. And this is very plain to see. You can see there's a definite shape here that seems to mirror the shape that we just discovered. And so this seems to be a normal distribution centered somewhere around here, and then the standard deviation, maybe we don't know what it is, but we could probably figure it out if we studied this data set. It does appear to follow this same general shape. And keep in mind that we can shift this around at will. We can change the mean to make it a different position on the x-axis, and we can stretch out the data and shrink it back close together. We can do all of that at will. We can apply all of those transformations by simply changing the mean and standard deviation here in our PDF. And so you can imagine that if we applied some transformations to that equation, we could get a curve that looks something like this. We could use a curve to model this situation. And then here, this is body heights reported by US men. This was just a self-reported example. And here we see kind of the similar shape appearing once again. You can see there's like a curve that looks something like this. It's a very similar shape to what we just derived. And look here, this is a little bit different. Here, this is molecular speed, and so they took samples of different gases. I think this was 800 degrees Kelvin. And you can see that all of these gases have different distributions, but they do all tend to follow this same general shape. You can see oxygen seems to have a much smaller standard deviation. All of their particles are sort of clustered more tightly around this mean here, whatever this is. And it's much less spread out than some of these other particles. But as the speed of the particles increases, and you might notice that as we move in this direction and the average gets faster and faster and faster for these particles, you can see that they actually are getting lighter. With hydrogen being the lightest, it has the highest average speed, but it also definitely has the largest standard deviation. This is very, very, very spread out. But all of these tend to exhibit the same shape as the SAT scores, as the body heights reported by US Mint. And right here, now this data seems to be skewed to the right. It seems like the vast majority of the data here is clustered around the lower end. And what this is actually a graph of is this is a graph of the proportion of people, or the number of people, I guess, that report experiencing symptoms of depression versus their age. And so you can imagine if we were to cut off this graph, so to speak, somewhere like here, then this would also seem to follow a normal distribution. It looks something like this. It's very tight, but it does seem to have the same curve that we're seeing with heights, that we're seeing with molecular speed, that we're seeing with SAT scores. And so this shape tends to crop up all the time in nature. You could think there's just tons of situations where there's the majority of data clustered around some mean that gets less and less probable as you move further and further away from the mean. Tons of phenomenon exhibit this shape. And if they don't, there is something called the central limit theorem that tells us that a sampling of that population, even if the population itself is not normally distributed, if we were to take the sampling distribution of that population with enough samples, you will get a sampling distribution that's normally distributed. And so what does that mean? We're going to have to talk about sampling, and we're going to have to talk about some other things before we can make that concrete. But just to build some sort of intuition as to the direction with which we're going, I have some graphs here. So if everything I said just now made no sense, just take a look at this population. So this population is clearly not normally distributed. We're not seeing this sort of bell curve shape that we're talking about, that we just derived with that probability density function for a normal distribution. This data does not exhibit that shape. And so that's what this is a graph of. This is just the population. It represents the frequency of some different values between 0 and 10. And you can see it gets less and less frequent as we get to 10, but this is sort of unidirectional. It just moves in one direction. This is not normally distributed at all. And then what is this? Well, this is the sample mean. So I took several samples of this data. I think at this one I took something like 15 samples, maybe 20. So I took 15, 20 samples of this data, and for each of those samples, I took the average and recorded it on this graph. And so every single one of these bars represents the average of this distribution that I got from sampling it several times. I think I used a sample size of like 1 in this case. And so this is what I got here. But as you increase the amount of times that you sample this data, as you increase your sample size, the data starts to look a little bit different. And so here you can see this is starting to look more normal. I sampled this data more times, and the graph of the sample means starts to look more and more normal. And so I think this was 50 times, but then I took 10,000 samples, and so let's see what that looks like. If you take the same distribution and you sample it 10,000 times, even though the distribution itself is clearly not normal, take a look at the sampling distribution. And so here, you can see that this definitely looks like a normal distribution, even though this population is clearly not normally distributed. So once again, if this isn't making sense, we're going to talk way more in depth about sampling in a future video. Maybe not the next one, maybe a couple more videos down the line, because we have to talk about some other things first. We have to talk about marginal probability density functions, joint probability distributions. We have to talk about confidence intervals and some other things. But this is just a sort of hint as to what's to come. This normal distribution is very useful. Even in situations where the data is not normally distributed, there's still a normal distribution at play. We could still use a normal distribution to model that data. All right, so we have 2 more things to cover with respect to the normal distribution, but now that the derivation is out of the way, this stuff will go pretty quickly. So we're asked what the standard normal distribution is. This is something you'll hear a lot in statistics. The standard normal distribution is just the normal distribution centered at a mean of 0 with a standard deviation of 1. And so the reason that we have a standard normal distribution is because people came up with this normal distribution. This expression was derived by Gauss for these. This probability density function was derived by Gauss back in the 1800s. And so before that, or in that time, we didn't have computers. And because this is a non-integrable function, they had to painstakingly come up with some sort of polynomial approximation or something like that. They had to figure out a way to compute this definite integral by hand using some method that's similar to how computers would compute this nowadays. But essentially, they just tabulated this expression right here, but for different bounds. And so they created a giant table full of different probabilities based on the standard normal distribution, which is just a normal distribution with a mean of 0 and a standard deviation of 1. And the reason they did that is because all normal distributions, regardless of the standard deviation and the mean, can be expressed in terms of this standard normal distribution by way of a z-score. And the z-score can simply be thought of as the number of standard deviations away from the mean. And it's useful because of this property right here that we have for normal distribution. So if I was to integrate this expression for the normal distribution centered at a mean of mu with a standard deviation of sigma, if I integrate that from negative sigma to sigma, essentially the probability of the data falling one standard deviation within one standard deviation of our mean here, this is going to be exactly the same as the probability of falling within one standard deviation of the standard normal distribution. And so a long time ago, people just computed this, and then they would express all other probability density functions or all other normal distributions in terms of a z-score. If they wanted to compute a probability for these, they would convert their probability to some sort of z-score, and then they would calculate that z-score, the probability of that z-score based on the standard normal distribution. So now we don't have to do that, although it is useful to do sometimes. Sometimes it's a little bit easier. But now we have computers, and computers are capable of computing things like this integral here. You don't have to do it by hand. So that's just one thing you might hear. You might hear about the standard normal distribution and z-scores. We're going to talk more about this. But this is just a little introduction to what these things are. All right, so here I have Desmos open. And so this is a graph of our standard normal distribution. This is with a mean of 0 and a standard deviation of 1. You can see it's a bit more spread out than the one that I showed previously with a standard deviation of 2, and that should be expected. The thing that I want to point out here is we can use Desmos to compute these integrals. So the first integral I have here goes from negative 1 to 1, and so this is computing the area underneath this curve from negative 1 to 1, and we get 0.682 blah, 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 etc. Now here I have another probability density function. This one has a standard deviation of 2. You can see the 2 is there, and as well in the denominator here. And instead of being centered at 0, this is centered at 1. If I wanted to graph this, I could take this piece out, and I could graph it here. And so here, this one is a little bit more spread out because the standard deviation is higher, and it's centered at 1. It's not centered at 0. And so this graph is a little bit different, but if we were to integrate over this from 1 plus 2, or from 1 minus 2 to 1 plus 2, since we have a standard deviation of 2 and a mean of 1, if we were to integrate this function, this probability density function, centered at 1, with a standard deviation of 2, from here we would be going from negative 1, or 2 units away from 1, to 2 units away in the positive direction, to 3. If we were to solve this integral, we're going to get the exact same value here. And so the probability of falling within one standard deviation of the mean is going to be the same for all normal distributions, regardless of what the standard deviation is and regardless of what the mean is. We have this equality here. And so this is what I mean. If we can compute how far away from the mean something is, if we can represent that, which we do in terms of a z-score, we calculate how many standard deviations away from the mean some data point is, then we don't have to use this equation here. We can solve for it in terms of the standard normal distribution. So I hope that's a little bit clearer now that we can see this inequality here. But for now, the thing that I want to focus on is there's one more aspect of normal distributions which is very useful and hammered in a lot in statistics courses, and that's this thing called the empirical rule. And so what the empirical rule tells us is that 68% of the data lies within one standard deviation of the mean for normal distributions. And so here you can see this is integrating from -1 to 1, the probability of being between -1 and 1, given a probability density function of the standard normal distribution. But this would be the same for all normal distributions. You would have to just adjust the bounds to be in terms of the standard deviations. The probability of being within one standard deviation of the norm is 68%. So you can see that here. 68.26, blah, 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 blah. What about the probability of being within two standard deviations of the norm? So if we want to compute this, we would just plug in -2 here to go 2 standard deviations away in the negative direction, and then +2 to go 2 standard deviations away in the positive direction. So that's this region here. And the area under the curve here is 0.95. So this tells us that there's a 95% chance of your data falling between 2 standard deviations, or within 2 standard deviations of your mean. This is true for all normal distributions. What about 3 standard deviations away? Let's see, we'll go 3 away in the negative direction, 3 away in the positive. Here we get 99.7% of our data is going to fall within 3 standard deviations of the norm. So this is where this sort of empirical rule comes from. And sometimes you'll hear it referred to as the 68, 95, 99.7 rule. This just tells us that one standard deviation within one standard deviation of the mean, we're going to find 68% of our data. Within 2 standard deviations, you'll find 95%. And within 3, you'll find approximately 99.7%. And so that's where this comes from. It comes from integrating this normal distribution PDF, this probability density function, with these bounds in terms of those standard deviations that we're interested in. And so I hope that's interesting. Rather than just asking you to memorize this, you can see exactly where it comes from. Hope you guys enjoyed this video. We're going to talk more about how we actually use the normal distribution in future videos. We're going to talk about confidence intervals. We're going to talk about lots of things that involve the normal distribution. Almost everything in statistics is going to sprout from this idea, essentially. Confidence intervals, hypothesis testing, lots of different distributions are going to be derived from this one. And so hope you guys enjoyed, and I'll see you all in the next one.